Hello. Okay. Good afternoon, guys. Today we're going to discuss about the PN junction diode, which comes under your unit 1. Okay, cluster group 1. So I hope that most of you have already gone through the module 0, which I post in Canvas. So how many of you have seen this? Uh, have seen this topic or video I have posted in the Canvas? So you can just write in the chat box so that I can check. You did. Chakravarti has seen. What about the remaining? Somebody is raising hand. Uh, so how? Please post in the chat box whether you have seen the video or not. So based upon the response, I will continue today's class. Okay. Uh, okay. Some of you have seen. Some of you did not. Okay. Anyways, from the average viewer analytics that I got is many of you did not see the entire video. The average viewer limit timings is only around 2 minutes. Okay, although the video lasts for 40 minutes. Anyways, I'll share the same PPT now, but however, I'll quickly finish that. Okay, stop posting your in the chat box now. You can stop posting. I'll share my screen. Okay, are you able to see my screen?
No, sir.
Yes, right. Okay.
Yes, sir.
I'll briefly
Yes,
give
sir.
my introduction to the review of semiconductor physics.
Yes, sir.
So in this topic, so you will be covering mostly about this intrinsic semiconductors. So these topics are intrinsic semiconductors, and then you have something to do with extrinsic semiconductors. Okay, so you'll be learning about the electrons, holes, and intrinsic semiconductor, and then conductivity, and then carrier concentration, holes in a valence band, and about the Fermi level, and then mass action law, and then in extrinsic semiconductors again you will be dealing about impurities, charge densities, and Fermi levels. Okay, so if you take a germanium crystal, this is the germanium crystal structure. So you know that what is the atomic number of germanium? I think I've already given you in the quiz, right? So I'll be randomly
32,
asking you
sir.
sum of 32, right? So germanium 32 for silicon
14.
14.
14.
Okay,
14, sir.
continue.
14.
Okay, okay. So germanium is 32, silicon is 14. So all these atoms are tetravalent. Please mute. Okay. So these are tetravalent. They have the valency. The valency is equal to 4. So are you able to see my writing? Can you
Yes, sir.
understand my writing? Okay, fine. Okay, so
Yes, sir.
they have valency 4 means they have 4 electrons in the outermost shell. So if you take a germanium crystal, they have 4 electrons, and then each electron will be shared by another germanium atom. So this electron 1, so this is 1 electron, this is 2, this is 3, and then you have 4. So each electron is shared with another germanium atom. So they're making up this covalent bond, right? So when they make this covalent bond, you will get this germanium crystal structure. And sometimes these covalent bonds are broken when there's some kind of thermal agitation. So thermal agitation is nothing but when you have a temperature, even at the room temperature, some of the weak covalent bonds will be broken down. Okay, so when such weak covalent bonds are broken, what happens? The electrons will be coming out of this covalent bond, and then it is called as free electron. This free electron will be moving all across the crystal structure. It is free to move. And these free electrons, existence of free electrons will contribute for the electricity. So as long as there are no free electrons, there will not be any electricity. Okay. So once this electron comes out of this covalent bond, this empty valency shell of this germanium atom will be now called a hole. So hole is nothing but absence of electron, or I can call it as a better term is a empty valency shell. Okay, so once the electron comes out of the covalent bond, a hole will be generated. Now, along with the electrons, even you can see the hole movement. So hole movement is apparent to your electron movement. So if you see this, let us say that we have a number of bonds are available here, and then you have a pair of hole and electron. So this one pair, this another pair, this another pair, and so on. Let us consider that one electron has released, has broken out of this bond, and then occupied a hole in the 6th place. From 7th place, it has occupied 6th place. Okay, now this is called as recombination. Recombination. So recombination means, so this a free electron is combining back with a hole. Okay, so this in this recombination, what happens? Now this will become another covalent bond, whereas at 7th place you now have a empty valency shell. Earlier the empty valency shell was present at position 6. Now it is present at position 7. It is as if electron, so electron has traveled from your right hand side, from this position 7 to position 6. When electron has traveled from position 7 to position 6, hole has traveled from position 6 to 7. Okay, so the direction of movement of your electron holes are opposite to each other. So there is no individual existence of hole. Okay, so it is only the absence of this electron in a covalent bond is termed as a hole. So if the electrons are moving from let us say from right hand side to left hand side, then holes will be moving from left hand side to right hand side. So in general, all the number of holes in an atom will be equal to number of free electrons. So you should stress on this free electrons, the term free. Okay, and then thermal agitations will produce new electron and hole pairs. So because of thermal agitation, or I can say temperature, existence of heat, new hole and electron pairs will be generated, and some of the electron hole pairs will be disappearing because of recombination. And this hole will behave as if it's a positive charge equal in magnitude to that of electron charge. And then now coming to conductivity. So you know that conductivity is nothing but current in per unit area, right? So it's a conductivity, current density. Current density J is nothing but your current per unit area. That is given by the expression J is equal to N into mu1 plus P into mu P into E epsilon, where N is the magnitude of electron concentration, P is the magnitude of hole concentration, and the mu and mu P are your mobilities, mobility of hole and mobility of electron, and the sigma is your conductivity. Okay. And then for a pure or intrinsic semiconductor, so intrinsic is nothing but, intrinsic implies pure semiconductor. So in this, number of electrons will be equal to number of holes. So let us consider this number as Ni, where Ni is your intrinsic concentration. Let us term it as intrinsic concentration Ni. This Ni will depend upon the temperature, and this is the relationship. You may not exactly know the equation, but you should always remember this kind of proportionalities. So Ni square is proportional to Tq, where T is your absolute temperature. So absolute temperature is nothing but your you should add 273 plus your whatever temperature in centigrade. Okay. And then coming to carrier concentration. So carriers are nothing but your electrons and holes. So in this topic, we'll be seeing about the carrier concentrations. So are you able to see my current slide, carrier concentration slide, or you are seeing any other slide?
Conductivity of a
Carrier
semiconductor slide has been showing, sir.
Okay. Actually, I changed the slide. That's why I have stopped in the middle. I'll just check. Okay. I think there's a delay between on the slide I am showing and the slide you are seeing. One thing I'll do, I'll just reshare. I'll stop sharing and then reshare. Is it visible now? Is my slides visible now?
No, sir.
No,
No, sir.
Okay, just a minute.
No, sir.
Okay, I think it is
Yes,
visible
sir.
now. Right. Okay. So this is the carrier concentration in intrinsic semiconductor. It is given by this equation. So if we have a, if you can see that this is the energy band diagram. So I'm enlarging it. Are you able to see the enlarged diagram?
Yes, sir.
Are you seeing this Fermi Dirac? Yes. Is it enlarged now? I think it is enlarged now. So you have this Fermi Dirac distribution diagram and energy band diagram. So in this, on the x-axis, you can see that 0, 0.51, right? Is the probability of finding an electron, or it's a Fermi Dirac function. On the y-axis, you have energy levels. Okay. So usually, a bounded electron should be present within the valency band. Okay. If an electron has to become a free electron, it should receive some energy. Usually the energy will be, it will receive from the thermal agitation. Okay. So when the electron receives the energy, this electron will receive the energy such that it can move and occupy the conduction band. Okay, so it will travel from the valence band and go to the conduction band. So when the electron leaves this conduction band, there will be the empty shell in the valence band, that we are calling it as hole. So holes will be, so you will find the holes in the valence band, whereas free electrons in the conduction band. Okay, so you will find the free electrons. So these are free electrons, and then you will find holes in the valence band. Okay, so when you want to find the intrinsic concentration of these free electrons and holes, should always identify that free electrons will be available in the conduction band, whereas holes will be available in the valence band. And then we are writing some kind of energy levels over here. So holes will be present between your energy level 0 and the energy level EV, where EV is the, I can say, the maximum energy level of your valence band. And then free electrons will be existing from energy level EC to initial above this EC. So I can take the limit as infinite. Okay, so these are the limits. So holes will exist somewhere between 0 and EV, and free electrons should be existing between EC and infinite. Okay, now we shall take this one energy band and diagram. So let us say that this is between the energy levels E and E plus DE. Okay, let us take energy band. So where we have the energy varying between E and E plus DE, let the number of electrons present will equal to Dn. Now this Dn is given by the equation N of E into F of E into dE, where N of E is your density of states. If you multiply this density of states with the Fermi function or the probability function, then you will get the concentration, carrier concentration. Okay, so if you want to get the total carrier concentration, what you need to do? You need to integrate this equation. So you have this equation Dn is equal to N of E into F of E into dE. So you need to integrate on both sides. Okay, so this will become this will be from 0 to n, and this limits will be between. So what will be the limits for the free electrons? So first we will be calculating this intrinsic concentration for the free electrons. Okay, so what are the limits for the free electrons? Can you see this energy band diagram?
EC to
What are the limits?
infinity.
EC to infinity.
EC to infinity.
Yeah, so that's why we are doing the integration from EC to infinity. Okay, so the density of state function is given by this term gamma into E minus EC power half. Okay, you need not know what is gamma as of now. So I think those things will be covered in depth in your semiconductor physics. So because of lack of time, we will not be able to cover all those things now. But however, you should remember that for the electrons, I am writing E minus EC power half, where EC is your reference energy level. Okay, whereas if I want to write the density of states for holes, then I would be writing for the holes, I will be writing gamma into EV minus E power half. Okay, in general, density of states is given by the equation gamma into E power half. This is the density of states function. But because we are writing the density of states between between these limits, so we will be writing the density of states as gamma into E minus EC power half. Okay, now we shall move to the next slide. So gamma is expression of gamma is given here. So are you able to see the next slide? Just check
No, sir.
if you are unable to.
No,
No.
sir.
Just a minute. I think the transition is taking delay in the Teams. Okay, I think now it is
Yes,
loaded.
sir.
Right.
Okay.
So this gamma will depend upon a term called Mn. If this gamma will be different from for your hole, and it will be different for your electron. Okay, this Mn is known as effective mass of electron. So the new term called effective mass will come in the quantum physics. In your classical physics, your mass m is always constant. You'll always consider, if you are writing a classical physics equation F is equal to ma, you'll always consider that m is as a constant term. However, in quantum physics, this m will not be a constant one. So mass will change along with its velocity with which it is moving. Okay, so a particle at rest and particle at motion will have two different masses. Okay, in order to simplify these equations, what they are going to do is they'll consider a term called effective mass. Okay, so in order to use the classical physics equations, instead of a constant term m, they will be using a new term called effective mass. So Mn is the effective mass of electron. Similarly, Mp is the effective mass of a hole. Okay. So the derivations are not necessary. You need not even remember this expression also. Only thing you need to know that gamma will depend upon effective mass of electron or hole. Okay. So and then if you do this integration, we will get the expression some n is equal to 10 into exponential of ec minus ef by kt. So we'll also explain this integration. So you have this Fermi function f of p is equal to 1 by exponential of e minus ef by kt, right? So first I'll write what is ne. N is equal to gamma into e minus ec power half, and then what I have, f of e as 1 by exponential of e minus ef by kt. See, in this expression, ef is called as a Fermi energy level. So ef is a Fermi energy level where probability of finding an electron is 50%. So at this level, at 0 degrees Kelvin, it will be 0.5. F of e is 0.5. Okay, ef is the energy level where the probability of finding an electron is 50%. So our f of e is 0.5. That is called a Fermi energy level, EF. Okay, in this expression, what they will be doing is they have to simplify this expression. In order to simplify this expression, they will be checking this denominator. So in this denominator, there are two terms. You have one, you have an exponent term, right? So you have E minus EF. So for electrons, electrons will be always in the conduction band, right? So electrons will be somewhere over here. So energy of electron, I can say that, I can confidently say that energy of the electron will be, E will be greater than EC. Okay. In such a case, I can also say that if I consider this term E minus EF by KT, I can say that the numerator is a large number because EF is a small compared to EC. Your E is somewhere over here. This is your E. I think there's a delay. Can you see the E that I have written over here?
Yes, sir.
Yes, okay, fine. Okay, E minus EF by KT. This numerator is a large number compared to this denominator. Okay, so when you have a large number, okay, this if you have a e power x, if x is large, what happens? If you have 1 plus ex, I can confidently say that 1 plus ex will be nearly equal to ex, right? So I will approximate this denominator to simply 1 by exponential of EF by KT. Okay. So what I will be writing? This term will be approximated to exponential of. So because this is 1 by e power x, this is something like 1 by e power x. So this I will write as e power minus x. So I will be writing, adding a minus symbol over here. Then I will be writing e minus ef by kt. Okay. And then I'll do the integration. I'll be showing the integration also. Just a moment. Because of the lack of time, I'll be showing the already derivation I have done. Is my page visible? I'm showing a PDF file. PDF file is visible?
No, sir, not yet, sir.
Sir,
Then I'll stop sharing and reshare again. I think there's some bug with the Teams app. For the past few days, I'm having some or the other trouble with this. Now, is it loaded?
No, sir.
no, sir. No, sir.
I think it is loaded now.
Yes, sir.
Okay.
Yes, sir.
Yes. Is it visible? Okay, fine. So we have done this till this step, right? So we have written it as gamma into exponential of minus EC minus EF by KT. Now, then we have got this expression. Now what we'll take? We'll take E minus EC as KT into X. We'll take some variable X, okay? Then this will convert, so if we differentiate this equation, what happens? dE will be equal to, because this is a constant value, we'll get d equal to kt into dx. So we are going to change the integral variable. So now the integral variable will be changed from dE to dx. So we'll be writing all those things. Then n will be, you will get it as, so unless you do it with hand, you will not be able to understand things, because this is a integration, definite integration. You should be very careful. So what we got? dE is equal to kt into dx. So we replace this in dE. So then what we got? N is equal to gamma into exponential of e minus ec minus ef by kt into integral. We have e minus ec to the power half. So in place of it, we will get kt power half into x power half into exponential of minus x. So this entire term we have taken it as x into, in place of d, you are writing kt into dx. Now the limits we have to change. So if we place e equal to ec over here, x will become 0. So this lower limit has been now become 0. And then if we place e equal to infinite, x will become infinite. So the integral has now changed from limits 0 to infinite. And if you bring this all those terms independent of x, we'll have an integral only in x, integral 0 to infinity x power half into e power minus x dx. And you know this standard expression for this integral, root over pi by 2. So finally we got an expression in gammas and exponential of minus of ec minus ef by kt, right? This term, entire term, we'll call it as nc, where nc is called density of states. So finally you will be getting this expression, n is equal to nc into exponential of ec minus ef by kt. So what I suggest you to do is, you go through this hands-on notes, you try it the integration on yourself. So you have to try the integration with your own hands, then only you will be able to understand the expression. Okay, so when you go after the class, you try that. Now this nc is equal to this expression. Okay, this nc is called as effective density of states in conduction band. Why it is conduction band? Because we are talking about free electrons. So free electrons are available in the conduction band. Okay, so I can write n is equal to nc into exponential of minus ec minus ef by kt. So this term I can always remember easily, because if I have the electrons in the conduction band, I will write it as nc. If I have for holes, if I want to write for holes, similarly I can write p equal to nv into exponential of, this exponential cannot be a large number. If the expression should be such that the exponential should result in a finite value, because the carrier concentration cannot be infinite number, right? So what I can always know that this exponential will be a some negative exponential, some e power minus x term will be there. So I'll write exponential negative of, and then I'll have some difference of energies divided by kt. This difference of energy is nothing but the limits. So one is the conduction band energy limit, other is your Fermi energy level. Out of these two, which one is higher? EC is higher. So I'll be writing for electrons, I will write EC minus EF. Similarly, if I want to write for holes, what I will be writing is P equal to NV into exponential of minus of. So if I go back to the energy band diagram for the holes, the higher, which of these two is higher energy level, EF or EV is higher? Which one is higher?
EF.
EF is higher. So what I will be writing? I can write P is equal to NV into exponential of negative term, so minus of EF minus EV by KT. The same procedure, actually you're doing the same kind of integration for holes also. Okay, then you'll be resulting. So for the holes also I have done. So as I told earlier, n is directly, we will write gamma into e power half. Here for the holes, the reference energy level is EV, and the holes are lying below the EV. So holes are below the EV, valency band level EV. So I will write it as EV minus E. Okay, so I'm writing it as gamma into EV minus E power half. Later on, For the only difference between these two integrations is that for the electron, I'm writing the Fermi function as F is equal to 1 by exponential. I have written expression, right? This is a probability of finding an electron. Okay, so if the probability of finding an electron is there, is f of e, then the probability of finding a hole will be 1 minus f of e, because these are two mutually exclusive elements, right? So if there are electrons are there, I mean to say that the hole is not existing, right? So when electron is not present, then only hole will be coming into picture. So for this Fermi function, it is we are writing, instead of f of e, we will be writing 1 minus f of e. Again, we will be doing that 1 minus 1 plus exponential or something. And then again, we'll take the denominator, we will reduce the denominator to a easier expression, and then we'll do the integration. Finally, we'll be getting this expression for holes. This NV is called as effective density of state function in valency band. Valency band because holes are existing in the valency band. So in the energy band diagram, electrons are in the conduction band, whereas holes are there in the valency band. Okay. And then for the intrinsic semiconductor, we have already written an expression, and now n is equal to P equal to Ni, right? Because number of holes and number of electrons are equal in a intrinsic semiconductor, and we are calling it as Ni. So we will equate the number of electrons and number of holes. So we have an expression for number of electrons, Nc into exponential of minus Ec minus Ef by kT on the left hand side. On the right hand side, we have Nv into exponential of Ef minus Ev by kT. Now what we are going to do is, we are going to get an expression for Fermi energy level. Okay, if you want to get the expression Fermi energy level, what you can do, you can directly bring all other terms to the right hand side. You have to do the logarithm on the both sides. So if you do the logarithm, you will be getting this expression. If you want, I can do the derivation also. So what you need to do is, you will take the Nc by Nv to one side, Nc by Nv, and you take this exponential to the right hand side. If you take the exponential to the right hand side, this minus will now become plus. So within the exponential, you know that e power e into e power b will be equal to e power a plus b. So here these terms within the exponential will be adding. So it will be ec minus ef. This minus on coming to this right hand side will become plus. Okay, and then you have minus of ef minus ev. So this entire thing divided by kT. Now Nc by Nv will be equal to exponential of Ec minus of minus is plus Ec by Ev, Ec plus Ev by kT, and then you have minus Ef minus 2Ef by kT. Now if you take the logarithm, it becomes log n Nc by Nv equal to Ec plus Ev minus 2Ef by kT. You take the kT to the other side, kT log n Nc by Nv equal to Ec plus Ev minus 2Ef. From this you'll get the expression Ef is equal to Ec plus Ev minus kT log n Nc by Nv. So all those things divide by 2. Okay, so you are remaining with this expression Ef is equal to Ec plus Ev by 2 minus kT by 2 into log n Nc by Nv. This expression also you need to remember. Okay, and then I'll erase all those things. So in this expression, if NC is equal to NV, what happens? What happens if NC is equal to NV? What is log n? Log n 1. What is log 1? Log 1
Zero.
is
0, sir.
0. So yes, this term will be disappearing. So you are left out with EF is equal to EC plus EV by 2. But then, see, if you see this NC and NV terms, if you check the NC and NV terms, so what you are having basically in NC or NV, you are having, if you check this entire term, so H, Planck's constant is constant, Boltzmann constant K is constant, temperature is also, I can take it as constant. So only difference between NC and NV is that effective mass. Hello? Please mute. Okay, I muted that. So only difference between NC and NV is with this Mn term. So I can say that EF will be equal to EC plus EV by 2 if and only if when the effective mass of hole and electrons are equal. So NC will be equal to NV when the effective mass of hole and electrons are equal. In that condition, you will get Fermi energy level is equal to average of your conduction band energy level and valency band energy level. So in the energy band diagram, this EC, this is EV. Here Fermi energy level will be exactly the average of these two values. So it is EC plus EV by 2. And this another case, so this is irrespective of the temperature. When both the effective mass are equal, then there is no point of talking about temperature. But in case if the NC is not equal to NV, if NC is not equal to NV, even in that case, if T equal to 0, if T is equal to 0, then what happens? If this T equal to 0, what happens? Again this term will become 0. Okay, so again you are left out with EF is equal to EC plus EV by 2. The same thing we have represented over in this energy band diagram. So can you see this diagram? At T equal to 0, you can see that EF is exactly between EC and EV. Whereas these energies are varying, this probability function is varying with the temperature. Okay, only at T it is irrespective of this values of Mn and Mp, you have this EF at exactly half. Next topic is intrinsic concentration and the mass action law. Is my screen visible?
No, sir.
No.
Yes, sir. Slide not, sir.
Slide loaded or not?
Previous slide is visible, sir.
Previous slide, sir.
Previous slide. No, intrinsic concentration. The slide intrinsic concentration is visible or not?
No,
Can you
sir.
see the
No,
mass
sir.
action la? No.
Not
No.
visible, sir.
Is it loaded? Is it fully visible or only partially visible? Because I'm seeing in my desktop a half screen. Can you see the full PPT?
Partially.
Partially
visible, sir.
Half, sir.
Now is it loaded?
No, sir.
Now is it loaded? Or only my desktop is shown?
Sir,
No,
only
sir.
desktop is
It's
shown.
not loaded.
I think it is now loaded. Fine.
Yes,
Can you
sir.
see the screen?
Yes, sir.
Right. So earlier we have expression for n, and then we have expressions for p. So what is n? If you remember, n is equal to, so n is for electron, nc into exponential of minus of Ec minus Ef by kT. Similarly, p equal to nv into exponential of minus of Ef minus Ev by kT. Now, if you do the multiplication of these two terms, so I'll get Np equal to Nc into Nv into exponential of minus of Ec minus Ef plus Ef minus Ev by kT. Ef gets cancelled. You'll be left over with Nc Nv into exponential of minus of Ec minus Ev by kT. Right? This difference Ec minus Ev is in the energy band diagram. This is your Ec, this is your Ev. This gap is nothing but your Ec minus Ev. This gap is known as energy gap. Energy gap. We are representing the energy gap by a term Eg. So Eg is equal to Ec minus Ev. So in this expression, when I'm writing n into p, I'm getting nc into nv into exponential of minus of Eg by kT, where Eg equal to Ec minus Ev. Okay, and then you already have this expression n is equal to p equal to ni. So if I multiply n into p, it will be equal to ni square. This expression is famously called as a mass action law. Okay, so product of your electron concentration into free electron concentration into hole concentration is always equal to intrinsic concentration square. This equation is valid even for extrinsic semiconductors also. This equation is famously known as mass action law. This you should always remember. This equation is valid even for your extrinsic semiconductors also. Okay, so this expression is valid only at a fixed temperature. If the temperature is varying, this expression will not be valid. Okay, at a given temperature, at a given fixed temperature, this product will be equal to ni square. Okay, so you already have this nc term proportional to t power 3 by 2. If you go back and see the expressions, then nc into you have the n into p is nothing but nc into nv. So therefore n into p will be proportional to t cube. This relationship you should remember. Okay, and then this energy gap will always decrease with the temperature. So that's why whenever you have an increase in temperature, what happens? The energy gap becomes lower, and then the electrons can easily travel from the valency band to conduction band. Because this energy gap gets lower the energy gap, it is easier for the electron in the valency band to reach the conduction band. So this the energy gap decreases linearly. So in order to represent the linear decrease, we are writing Eg as Eg naught minus beta into T, where beta is your slope. So it is as if your energy gap is decreasing in this fashion. Okay, this is your Eg naught. The slope is equal to beta. Slope beta is at T is equal to 0. Your energy gap is Eg naught. As the T increases, energy gap is going to decrease. On the y-axis, you have your energy gap Eg. Okay. So energy gap decreases linearly with temperature, and given by the equation Eg is equal to Eg naught minus beta T. Okay. And then okay, now ni square will be proportional to T cube into exponential of, in place of Eg I will be writing Eg naught minus beta T by kT. Okay, and again this beta term, so this will be proportional to T cube into exponential of minus Eg naught by kT. I can again write into exponential of, I will again the one exponential into two parts, exponential of beta T by kT. This tt gets cancelled, it's beta by k, right? So in order to write this entire this term, this is a exponential beta by k is a constant, and then you have again the proportionality is there. So I can directly write, in place of that I can write a proportionality constant a naught. So you can only simply remember that ni square is proportional to T cube, and this proportional to exponential of minus Eg naught by kT. So that's it with your intrinsic semiconductor. So in the intrinsic semiconductor, what we have seen, basically we have seen the concentration of N, and then concentrations of P, and then we have seen N into P is equal to Ni square. Okay, and then if we come to the extrinsic semiconductor, in the extrinsic semiconductor what happens? we are adding some impurities. So impurities can be pentavalent impurities, or you're not getting my voice. Hello? So is it everybody is not getting my voice, or only few people? Am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Sure.
Sir.
Okay, fine. I think some people may be having network issue. So either we have a pentavalent impurity or a trivalent impurity. So when you're adding pentavalent impurity, what happens? You have an excess electron. So usually you should have 4 electrons in the tetravalent structure. When you have this excess electron, this electron is now not bound by any of the covalent bonds. See, now it is nothing but a free electron. So because of this addition of donor impurity, we are getting excess of free electrons. Okay. Why we are getting this excess of free electrons? Because donor atom energy level will be close to your conduction band. Okay. So this donor energy level, this dotted line, will be close to the conduction band energy level. And because of which, it is easy for the electron of the donor atom to reach the conduction band. So for electron to reach from valency band to conduction band, it takes more energy. So you need to pump in more energy, or you need more thermal agitation. Whereas a electron belonging to the donor atom can easily reach the conduction band. So this donor atom will contribute for excess of free electrons. These free electrons will be roaming all across your crystal structure and then contributing for the conduction of electricity. Okay. So this energy required will be only 0.01 electron volts if it's for a germanium crystal. It will be only 0.05 electron volt if it's for a silicon crystal. Okay. So that is very much less compared to that of a energy required to kick this electron from the valence band to the conduction band. Now what happens? So instead of the electrons from valence band, most of the electrons that are sitting in the conduction band now belong to the donor atoms. Okay, they do not belong to the your germanium crystal, but they belong to the donor atoms. So I can say that the number of electrons in the conduction band concentration will be nearly equal to the concentration of your donor atoms. Okay. Similarly, if you take a trivalent impurity, so when you have a trivalent impurity, like here I am taking a indium. So what happens? So you have you do not have one electron for forming a covalent bond. So this is the absence of your electron. This I can call it as a hole. So this is the energy level of your acceptor ion. So electrons will try to, so electrons of the other atoms will try to reach this hole. Okay, if electron is there in the valence band, these electrons will recombine with the holes in the acceptor energy level instead of reaching the conduction band. To reach the conduction band from the valence band, more energy is required. Instead, for the electron to reach the acceptor energy level, it takes less energy. Okay, so obviously most of the electrons will be easily reaching the acceptor energy level. And also you can see that only 0.01 electron volt is required for electron from valency band to reach the acceptor energy level. Okay. So what happens? So more number of holes will be near to the valency band energy level. And then you have number of holes will be nearly equal to that of concentration of acceptor impurities. So you have two equations. N is nearly equal to donor atoms, P is nearly equal to acceptor atoms.
1, 2, 3, 4.
ఏంటి 1 2 3 4 టైం అయిపోయిందమ్మా. ఎవరు పాట పాడుతున్నారు? ఓకే. So I'll finish this remaining topics in the next class. So you are left out with some more topics in the review of semiconductor physics. So I think only 2 slides are left, which I'll cover in the next class, and then we'll move on to the PN junction diode. Okay, because some of you are not have seen the video that I have already uploaded. I'm just repeating the same thing. Okay, so please go through the module in which I have kept this video on review of semiconductor physics and attempt the quiz that is posted. Okay, I'll now take the attendance and then I'll stop the class. So those who are joined after 3 o'clock, they will not get the attendance.